Cool. Thanks, Harry. So yes, thanks everyone for listening. Cool. So yeah, as Harry says, my role as a research software engineer is to try and help our users make use of the HPC systems that we have. And I guess my role over the next couple of days is to try and take all of the information that I've learned about MPI in the last few days and try and do something useful with it, which is going to be something of a challenge. So Cambridge has a very long history of doing computing. Starting from this very early machines, one called EDSAC, which was developed by someone called Wilkes at the University of Cambridge, whose name lives on in one of our current machines. The University of Cambridge, is quite a long time before I can officially say we, have been working on these kind of systems. EDSAC was the first, up on the top. The one in the bottom left, EDSAC2, was after industry got involved and then suddenly got a lot cleaner and a lot less researchy looking. And on the bottom right is a Titan machine, which is notable in that it has a bunch of researchers queuing to use a scheduler or to try and get onto the machine and ask the scheduler for access, but in this case the scheduler is an actual human rather than a nasty Slurm instance. And whilst these machines were pretty cutting edge in their time, I think the apocryphal quote about them is that EDSAC in particular sometimes worked for more than 24 hours, and we in general try and do a little bit better than that nowadays. So now, being part of an old university is good in many ways. Cambridge has been around for 800 years, and a lot of the infrastructure of Cambridge has been around for 800 years, which is great, but not necessarily so great for hosting data center. And in the last few years, we've been able to move out of the center of town, out of where we were hosted in an ancient old building, into a custom data center, which means that instead of being in a situation where we were limited on simultaneously on floor space, on floor weight, on power and cooling at the same time, we've now in a more sensible and less disaster-prone environment where we can actually have a modern and sensible-looking water-cooled data center. So we have a very complicated environment of users and systems. We have at the top here a bunch of different user communities from different national and local services that try and use our systems. And down the bottom we have HPC systems and a bunch of other things that we use to try and provide services to the various user groups. We have HPC systems. We have alongside that cloud infrastructure that uses OpenStack to try and present a more flexible infrastructure to our user groups, as well as a whole bunch of storage that comes in the different flavors of speed and capacity and resiliency. And one of the things we've been trying to work towards is to combine all of this into one big service that means that we can take different parts of what we need. If we need a high performance compute system and a bit of storage, we can put that into a service and then present that to a user. And if a user wants to combine some more modern, I hesitate to say, infrastructure using perhaps VMs and web services, they can take that, combine it with HPC, and make a useful scientific service on top of that. I mean, in general, HPC is a bit odd in the current environment. We still talk about machines with names. We have Peta 4 and Wilkes 2 or R2 machines. But if you log on to AWS, you don't have a machine called the Jeff Bezos machine, or you don't log on to the Sergey machine from Google. These are completely abstracted away. And so we're trying to kind of work in that same direction where we're giving users access to a platform rather than to a bunch of hardware. So one example of this that we've done fairly recently is for a use case of a smart cities thing where people want to be able to interact closely with a complicated data ecosystem where they can look in their browser at a complex simulation output, interact with it by clicking on stuff. That goes through a cloud service made available through OpenStack, and then on the back end that fires jobs into our HPC systems to go and simulate the next phase of that simulation, and then that next data gets fed back into the front end. So ideally, the user doesn't need to know that they're running against a GPU cluster or a CPU cluster. It's all just a thing that happens or a workflow that happens. one thing we've done recently as well that you never hesitate to brag about is that we built a large flash storage device that got us to #1 in the world on the IO 500 benchmark. It's fairly rare that a relatively small university in a particularly small country gets to #1 in the world at anything at the moment. So we are pleased to be able to say that this is something that we've done particularly well. And in the last ISC, we managed to beat Summit into first place with this piece of hardware that achieves some fairly large numbers of 500 gigabytes a second and many millions of IOPS. And we hope that this kind of infrastructure, flash storage sitting in between our HPC system and our more classic storage, is going to be useful for a bunch of applications in the future. I mean, one thing that would be useful with this kind of thing is that when we're looking at benchmarks that really push the IO system to try and get the maximum performance out of it, is that we don't often have a lot of the tools that we're used to as application engineers when we're looking at performance of applications to look at the performance of systems. And it would be nice to have some better understanding in tools like INAM, for example, which offers a bunch of really interesting ways of looking at what your system's up to. It'd be interesting to see the storage traffic as well appear in something like that. So our large CPU system is called PETA-4. It's a fairly standard workhorse Skylake system. It was, since 2017, the largest system in the largest university system in the UK, measured by Limpac, for whatever that's worth. And alongside the Skylakes, we also have a KNL partition, and the whole thing's connected together with OmniPath. So we have not been served particularly well by Intel's recent decisions to drop all of their technology. But we hope that it will still have quite a fairly long life ahead of it. So, in terms of the MPI performance, one thing that I've been looking at in preparation for this is the performance of MVAPICH on our OPA system. And as expected, it works fairly well. I mean, I, to be honest, was somewhat unaware that MVAPICH team had put the effort into making it work well on OPA, and was pleasantly surprised that it did work pretty well. And as you can see, I'm comparing MVAPICH, OpenMPI, and Intel MPI, and the results are pretty much of a muchness. There's nothing particularly exciting to see here, apart from the Intel MPI is surprisingly bad. You would think that Intel, with their own MPI and their own network on their own sockets, might be able to produce something that works pretty well out of the box, but it's significantly behind the rest of them. There's this little bump at the 16K message size, which I think Nick also identified in his talk. And as there's a gap between MVAPICH and the others there, I guess that represents an opportunity for a little bit of tuning. Probably fairly straightforward. So zooming in on this a little bit to try and find some more interesting difference. So we look at the small message size and also draw out the error bars that kind of show the maximum and minimum that I found over a large number of runs of OSU. You can see that there is a slightly more pronounced difference. And in particular, there's at the top end, at the sort of long tails of bad performance, these go quite a long way beyond where we'd expect. So looking at the red line, the MVAPICH2 line, we can see that the best performance that we hope for is a bit less than 1 microsecond, and that goes up to, what's that, about 1.1. This all seems quite good. And the other end is Intel MPI, which starts at 1.3, but goes up to beyond 2 in some cases. And I would expect that with the kind of applications that we run, tightly coupled and closely synchronized kind of applications, the performance is going to be largely dominated by that worst case rather than the best case. And this is something I didn't really expect to see, that there'd be such a spread. I was expecting something a bit more like the MVAPICH result, which has a boring little spread that can probably be explained by kind of operating system jitter or something equally dull. But the Intel MPI one, where it's going by a factor of 2, is rather more concerning, because I think that would probably have a visible effect on actual applications. And I'd be interested to know what kind of methodologies people use for looking at these kind of statistics in a larger scale, rather than just running a bunch and looking at the best and worst cases. So, in terms of actual applications, the application that we chose to look at for this is CASTEP, which is a DFT code, a materials or electronic structure code, which was originally from the University of Cambridge and is relatively similar to Quantum Espresso and VASP and the whole host of other DFT codes that are around. It's one of the codes that uses a large amount of our overall compute time, so we are deeply invested in its performance, and even a small percentage improvement in the performance of CASTEP in the UK ecosystem has a fairly outsized return in the amount of resources it uses. So we looked at 5 test cases with increasing scale. It's not really possible to do a pure weak scaling with something like CASTEP, but these kind of represent the breadth of what we think the science community is likely to use. They go up in increasing number of atoms, and they also go up in increasing number of nodes to try and keep the workflow fairly constant. Normalize the runtime to the MVAPICH result, and you can see that in this case, we see that MVAPICH is generally the winner, Intel MPI is generally the loser, and OpenMPI kind of bounces around between them. It's particularly notable that at the larger test cases on the right, which are at 16 and 32 nodes, the differences are becoming more pronounced. In fact, the difference between MVAPICH and Intel MPI is heading up towards 1.8x, which is huge considering the amount of people that use the code on this system. So the design of CASTEP is such that it tries to solve its equations in a way to get the best floating point efficiency. It was designed originally in the 90s, I think, and so it's pretty much a product of its time. It's one of these DFT codes that chooses to solve the Schrödinger equation by Fourier transforming into k-space, using a linear solution in that, and then transforming back. So this means that all of the hard work is done by the FFT and BLAST libraries, or LAPACK libraries, which is great as far as getting good floating point efficiency on single nodes, not so great as far as getting good scaling efficiency, because you end up doing large FFTs and lots of all-to-all type communication patterns. The other fun feature of these kind of codes is that as you go to larger scale, more atoms, the amount of parallelism that is available starts to decrease. So as you go to larger scale, you end up struggling to find more parallelism to put into the code, which means that you end up with less efficient the larger scale you go to. So the other one we looked at is GrowMax, which I think a few people have mentioned so far today. Looked at a bunch of test cases, again at different scales, trying to keep them at sensible scales that our users might actually run. So we got from some standard test cases, the MEM, RIB, and PEP ones, as well as the homegrown one that Nick already mentioned from the UK biological simulation community. And again, slightly surprisingly, in my experience, there's actually a pretty significant win towards MVAPICH rather than Intel MPI. And on both of these applications, I was kind of expecting to see that the MPI libraries were going to be pretty much of a muchness. There may be one would win slightly on one benchmark and would lose on another. And this is not what I've seen at all. But in fact, there's a kind of strong preference for MVAPICH on every one of the benchmarks, and not by a small amount. We're approaching 2x here, and also on CASTEP as well. And these are quite different codes. So somewhat concerning that we haven't made this our default and told our users about it until, well, tomorrow. So, changing tack slightly to our GPU machines, we were a fairly early adopter of GPUs in an HPC system. We started in 2009 with a relatively small system, and then in 2013 and 17 got upgrades to that system. And since 2013, we've had the largest GPU system in the UK, which says a lot more about the UK's science funding than it does about the size of the GPU system, because they're both relatively small. We're pleased to get both of them into the Green 500, into the top 5 when they first were released, and still does fairly well now. We're looking now at what we might put together for our next iteration of this machine, possibly in 2020 or 2021, depending on how the roadmaps come together. But I mean, the design of these GPU systems is still something of an open question, right? I mean, Nvidia has its own designs with NVLink, which are great, but this is a kind of change in direction from where we've been seeing things go with PCI Express in the past. And looking into the future where other companies will have other accelerators that will connect to other different buses, this is going to be more of an open question as we go forward. So in our first iteration, we chose a design with K20 GPUs and Ivy Bridge CPUs at the time, and an FDR interconnect. This caused us a great deal of problems with things like binding and placement, and trying to get the MPI libraries to understand which device to talk to, which GPU should be bound to which NIC. I mean, it ultimately worked, and with the help of the guys here at the time and with others, but this was a constant source of problems for our users. It also meant that we couldn't get our scheduler to understand this, and so we could only give people resources at the granularity of nodes. So we couldn't share nodes, and people would like to run jobs on single GPUs rather than two. So when we went for an upgrade, we chose a slightly different design where instead of having this dual socket, we had a single socket connected to a bunch of GPUs and a single NIC. This removed all of the tricky NUMA and binding and so on effects and made everything quite a lot simpler. Also meant we could do node sharing and give people single GPUs rather than all of the GPUs at once, which made our users quite happy. And this kind of design is extremely efficient in terms of GPUs per dollar. There's very little overhead in terms of CPUs and networks that aren't ultimately adding to your top 500 score. However, there's obviously a very big drop in bandwidth per flop between them. We went from K20 to P100, which has a something X increase in the amount of flops, and we went from FDR to EDR, which is slightly less than 2X increase in the number of bytes per second available. And as we went from 2 to 4 GPUs, I think this was something like an 8X reduction in network bandwidth per flop, which we were very concerned about might be something that would very much limit the scalability of the system. Turns out that wasn't something worth worrying about at all. 4 GPUs is actually quite a lot for most of our users. 8 or 16 GPUs is also an enormous amount, so people don't really try and use that much of the system at huge scale, at least for the kind of workloads we're looking at. So the scalability was not a problem for us. For the future design, we're looking at something more like this, where we have probably a hybrid of the two, where we have more GPUs and we go something back to a twin socket design, just because there's unlikely to be any designs that would allow us to have a PCI Gen 4 PLX switch at the moment. So we're going to have something like this and hopefully get something of the best of the both worlds. We'll have a very scalable design with lots of network bandwidth, and we'll also have a fairly efficient design in terms of number of GPUs per dollar spent on the system. So the kind of applications that run on these systems are a combination of the well-known ones like GrowMax, as well as some homegrown applications, namely TurboStream, which is an application from Cambridge that does simulation of turbo machinery and been relatively successful in using lots of our GPU time over the last few years, and PyFR, which is from Imperial College in London. That is another CFD application, and I think won a prize quite recently. And both of these applications are strongly dependent on the latency of their halo exchanges between the parallel workers, and this is something that we've seen MVAPICH GDR has a very useful contribution to. On the right is a micro benchmark we extracted from TurboStream, where they're doing something like a halo exchange. It's not quite the same because it's all unstructured mesh, and there's a bunch of workers that have to aggregate results before being sent. But in both the large case and in the small case, which in terms of large amount of network traffic and small, we see an advantage from MVAPICH GDR and a larger advantage when we go down to smaller sized messages. So the last thing I was going to talk about is RoCE. So RoCE, if anyone who doesn't know, is a standard that allows Ethernet devices to perform the RDMA kind of actions that we expect from InfiniBand and other high performance networks. And Rocky is a layer that if you have a capable NIC, you can turn it on and you get an extra device, an extra network device that looks a bit like an InfiniBand device and can be used as such. It has a lot of the features you'd expect from an InfiniBand device, but some, in our case, multicast appears to be missing, which makes things slightly confusing. Why we're interested in doing this is that we're somewhat sad to see the demise of OPA, and we would believe that competition between the HPC vendors is a relatively good thing. And so the current situation where Mellanox and Cray have the world to themselves is, in our opinion, my opinion, not necessarily a good thing, both in terms of the technological innovation. We'd like some sort of white heat of competition to try and drive things forward as quickly as possible, but also in terms of price competitiveness, especially for us relatively small users who'd like to buy these relatively small systems. The other aspect is that a lot of our workload is not running at the kind of huge scale that we'd expect from kind of flagship or leadership class HPC centers. Our median job size is between 4 or 8 nodes or so, which means that perhaps we don't need some of the extreme scale performance that is available from the Mellanox or Crays of this world. And so we'd like to investigate whether we could get reasonable performance on our actual application workload using some of this cheaper, more standards, more open technology. So the test bed that we built for this is 192 nodes of our Skylake system, and gave them dual 25 gig Ethernet cards. And the first open thing about it is that we can mix the vendors of the network cards and the switches. We have Dell switches and Marvell network cards, and they work together just fine, mostly. So the synthetics that you get from Rocky are fairly uninspiring in a way. Including our OPA as a baseline, which is around 1 microsecond at the small scale. And we can see that the Rocky achieves between, this is a log scale, so that's 4 and 6 roughly, microseconds at the small message sizes. MVAPICH is doing slightly better than OpenMPI immediately, which is always nice to see. And we can also see at the top end, at the bandwidth dominated regime, there's something a bit suspicious where the OpenMPI Rocky curve crosses over to join the OPA curve. So that, I guess, is either telling me that, well, it's telling me something's gone wrong there in one of the libraries. So this is all fine. 4 microseconds is not as good as 1 microsecond, but the key point is, does this actually matter for the kind of applications that we're looking at? And I guess the answer is maybe. So we're going back to the CASTEP benchmark that I looked at before, and again including the OPA as a baseline. You can see that for the small scale, the TIN benchmark, which is 2 nodes, see there's almost no exciting difference between them. We go to a larger one, which is 4 nodes in this case, the AL3, there's a much more exciting difference that we're going to, well, about 1.5x the runtime, and 2x in the case of OpenMPI. And then we keep going to larger benchmarks. The solid benzene one, which is 16 nodes, I think, has MVAPICH is kind of hanging in there on the Rocky system, but OpenMPI has kind of gone off into some sort of exponential decay up there. And by the time we get to the big, and by big I'm meaning like 32 nodes and 48 nodes in this case, their Rocky just doesn't make any progress at all.
Quick question. So what is the communication pattern used in CASTEP?
So it depends on the problem size, but at these large ones where the difference is getting more interesting on the right-hand side, it's pretty much like a large FFT. Okay. So all-to-alls and the same as, well, many other codes, I guess.
So did it just die or did it hang?
It got stuck in its startup where it does a kind of boring other calculation before it gets going. And I waited for a few hours and decided that it wasn't doing anything. I investigated into exactly what it was doing when it got stuck. I mean, it was making progress. It wasn't fully hung. It was just making progress slowly enough that it wasn't worth waiting, I decided. So the other benchmark, GrowMax, you see for the small scale, the 2-node thing, everything seems to be fine. We get a small performance degradation. We go up to slightly larger node counts. I think we're talking about 8 for the RIB case, 12 for the PEP case, and then 16. They either didn't run or was amusingly slow. So the GrowMax one should be easier. It's a bit more point-to-point calculation. I would expect it wouldn't suffer from things like collectives that just haven't been exposed to this kind of hardware before. So there's more investigation to go there, I guess, in what's going on. But overall, we see the Rocky results as actually fairly kind of hopeful. Things basically work. And for a large amount of our high throughput kind of work, this would be good enough to a large extent. We just have to train our users to choose workloads that are sensibly sized for the kind of hardware that we have. So, obviously I was hoping to be able to come here and say that MVAPICH is great, because it would be rude otherwise, but I was really found that it did actually do great, which was nice to see. The Rocky stuff works-ish, but you probably don't want to use it. And if you do, use MVAPICH because it's better than OpenMPI. And thanks to everyone.
Let's thank the speaker.